We are studying the sixth paper, Calculus of Several Variables. Right now, we are going through the second chapter, Calculus of Scalar Fields. In the first module, we discussed limits and continuity of scalar fields. Now, we shall start our second module. In this, we shall discuss partial derivatives. We start with stating the learning objectives. After studying this module, we shall be able to know what do we mean by partial derivatives of scalar fields, higher order partial derivatives of scalar fields. Then we shall study mixed partial derivatives and show that they may not be equal. Then we shall discuss geometric interpretation of partial derivatives. Finally, we shall try to find an answer to the following question. If at an point of a scalar field all the partial derivatives exist finitely, can we say the function is differentiable at the point? We recall from our study of calculus of functions of a single real variable that a function f from a to r, where a is a subset of reals, is said to be differentiable at a point c, where c is an interior point of the set A, if and only if the limit f of c plus h minus f c by h as h tends to 0 exists finitely. Here we have given a small increment c plus h to the independent variable c. We have to take care that c plus h should be in A. We can always find such h because c is an interior point of the set A. The corresponding change in the dependent variable is f of c plus h minus f c. Then we consider the ratio f of c plus h minus f c by h. So, it gives us the average rate of change of the function. Then we take its limit as h approaches 0. If the limit exists finitely, its value is called the derivative of the function f at the point c. The usual notations are f dash c or df dx at the point c. That is, f dash c equals limit of f of c plus h minus f c by h as h approaches 0. Now, let us make an attempt to extend this concept to cases where the number of independent variables is more than 1. Our aim is to find a suitable notion for differentiability for a scalar field when the number of independent variable increases from 1 to more. We shall start our discussion from cases when the number of independent variables is 2. Then we shall generalize it for any natural number n. We consider a scalar field f defined on a set D which is a subset of R2. We consider any point AB which is an interior point of the set D. We try to imitate the definition we used for derivative of a single real variable. We give an increment hk to the vector AB. So, AB goes to a plus h b plus k. Then the change in the function is f of a plus h b plus k minus f a b. Like the previous case, we write f of a plus h b plus k minus f a b divided by h k and try to find its limit as h k approaches the origin. But this does not make any sense, because if we look at the numerator, f of a plus h b plus k and f a b both are real numbers. So, their difference is another real number which is properly defined. But division of a real number by a point in R2 is undefined. So, we have no natural generalization of the concept of derivative of a function of one variable in this manner. But our target is to get something that is sensible. Moreover, it should admit our known notion of derivative of a function of a single real variable as a particular case. We consider a scalar field f defined over a set D which is a subset of R2. We suppose the variables are x and y. If one variable, say y, is kept constant, then we can consider it as a function of a one variable x. So, we can try to find the derivative of f treating it as a function of one variable at some point a b which is interior to the set D with respect to the variable x. This result is termed as the partial derivative of f with respect to the first independent variable x at the point a b. If the limit exists, we denote this by f x a b or del f del x at the point a b or d1 f at the point a b. So, del f del x at the point a b or d1 f at the point a b is the limit of a plus h f of a plus h b minus f a b divided by h as h approaches 0, provided the limit exists. In a similar fashion, the partial derivative of f with respect to the second variable y at the point a b is denoted by f y a b or del f del y at the point a b or d2 f at the point a b, and is defined by d2 f at the point a b or del f del y at the point a b is limit of f of a b plus k minus f e a b divided by k as k approaches 0, provided the limit exists. In this case, we kept the first variable x as constant. As we told earlier, we now generalize this notion for scalar valued functions, that is scalar fields, where the number of variables is 2 or more. Let D be a set in Rn, f is a scalar field defined on the set D, and C is an interior point of D. As C is a point in Rn, we can express C equal to the ordered n tuple C1, C2 up to Cn. Now, for each I running over 1 to n, the partial derivative of f with respect to the ith independent variable xi at the point C is denoted by f x I c or del f del xi at the point C or dif at the point C, and is defined to be the limit f of C1 up to Ci minus 1, Ci plus h, Ci plus 1 up to Cn minus Fc by h as h approaches 0. We denote this by del f del xi at the point C, provided the limit exists. So, what we do here, we keep n minus 1 variables unchanged and change only in the ith variable. So, the in case of the ith variable Ci changes to Ci plus h. Now, how to calculate partial derivatives? Let f be a map defined over a set D which is a subset of Rn, and C is an interior point of the set D. We assume that del f del xi exists at the point C for some I from the set 1 to up to n. From the definition, of partial derivative, it is clear that in order to calculate del f del xi at the point C, we treat all the remaining variables as constants and differentiate f with respect to the variable xi at the point C. So, we find that partial derivatives are easy to calculate. We earlier studied that in case of ordinary derivatives, that is, derivatives of real valued functions of a single real variable, satisfies some properties like linearity properties, Leibniz properties, and moreover, differentiability implies continuity. Right now, we check whether these are true for the case of partial derivatives. We find that partial derivatives satisfy linearity and Leibniz properties. Let f and g be two scalar fields defined on a set D, where D is a subset of Rn and C is an interior point of D. We further assume that both the partial derivatives del f del xi and del g del xi exist at the point C for some I from the set 1 to up to n. Then we have the following properties. The partial derivative of f plus g with respect to the variable xi at the point C equals with del f del xi at the point C plus del g del xi at the point C. That is, partial derivative of sums equals with sum of partial derivatives. Similar thing happens when we consider difference of the scalar fields f and g. We find partial derivative of f minus g with respect to the variable xi at the point C equals with del f del xi at the point C minus del g del xi at the point C. That is, in case of partial derivatives, derivative of difference equals with difference of partial derivatives. Next, let be any real number. We consider the function a f. Clearly, it is another function defined over the set D and is real valued. If del f del xi exists at the point C, we can find the partial derivative or the function a f with respect to the ith variable exists at the point C, and moreover, del del xi of a f at the point C equals with a times del f del xi at the point C. Finally, we discuss regarding the product functions. We find that the partial derivative of the product function f g with respect to the ith variable at the point C equals with del f del xi at the point C multiplied by g c plus f c times del g del xi at the point C. This is what we mean by Leibniz property. Thus, we find that for a scalar valued function of a single real variable to be differentiable at a point of its domain, it is a necessary condition that the function is continuous at the point. But this is not always true in the case of partial derivatives of scalar fields. That is, a scalar valued function of several variables can have partial derivatives at a point of its domain with respect to each variable, but not continuous at that point. For assurance, we give an example. Let us consider the following scalar field. F is a real valued function defined over R2 as follows. Fxy is x square y divided by x to the power 4 plus y square if xy is different from origin. otherwise it is 0. Now first we fix the second variable y and consider the first partial derivative. We find del f del x at the point 0 0, which is limit of f of 0 plus h 0 minus f 0 0 by h as h tends to 0, which is nothing but 0. Similarly, we now fix the first variable. We find del f del y at the point 0 0 is the limit of f of 0 0 plus h minus f 0 0 by h as h approaches 0, and it is found to be 0 also. Thus, both the partial derivatives of f exist at the origin. Now, we shall see that the function f is not continuous at this point. We approach the origin along the path y equal to mx square, that is a parabolic path for some m in R. We find that limit of f x y as x y approaches 0 0 is limit of f of x mx square as x tends to 0. So, this equals with limit of mx to the power 4 by x to the power 4 plus m square x to the power 4 as x approaches 0. And eventually, we find the value of the limit is m by 1 plus m square, which is different for different values of m. But we know that value of a limit, if exists, must be unique. So, the limit of f x y as x y approaches the origin does not exist. So, the function is not continuous at the origin. In the previous example, we found that both del f del x, del f del y exist at a point. However, the function was not continuous at that point. We have the following remark. For a scalar valued function of n variables, f from D to R, where D is a subset of Rn, the existence of the partial derivative dIf at the point C, that is del f del xi at the point C of f with respect to the ith variable xi at the point C, implies the continuity of f in the variable xi only. But this does not imply the continuity of f with respect to all the variables x1, x2, xn simultaneously. In the case of partial derivatives, the main obstacle is that whenever we consider a partial derivative, we confine ourselves to exactly one variable at a single instance. Now, let us recall the geometric interpretation of ordinary derivative. Let f be a function defined in some neighborhood of a point C. If f dash c exists, then we know that it gives the slope of the tangent to the graph of the function f at the point C. Now, we shall find the geometric interpretation of partial derivatives. To have a geometric interpretation, we confine ourselves to dimension 2. Let D be an open connected set in R2 and f is a scalar field defined on D. The graph of f is defined by the collection of all ordered triplets x, y, f x y, where x y is a member of D. Clearly, it defines a surface in R3. Now, through every point on this surface, one can draw many straight lines tangent to the surface. Two of them are of special importance. If we fix x and let y vary, then it is a function of y alone. So, it will give us a curve which lies entirely on the surface. We call such a curve a y coordinate curve. Similarly, we can fix y and draw an x coordinate curve. Finding partial derivative can be considered a process of taking these tangent lines which are parallel to the axis and then finding its slope. Basically, partial derivatives give us the instantaneous rate of change of a function in the directions of the coordinate axis. Now, it is time to discuss higher order partial derivatives. Let D is a subset of Rn. For the sake of convenience, we consider D as an open set. Let F is a scalar field defined on R. If the partial derivatives of F exist, all of them are new functions defined on D. So, we have n many functions del f del x1, del f del x2 up to del f del xn or d1f up to dnf. All of them have domain D and are real valued. So, we can consider their partial derivatives provided they exist. The resulting functions are termed as the second order partial derivatives of f. So, the second order partial derivatives of f are denoted and are defined by the following: dij of f at the point C is f xi xj at the point C. Another notation del 2f del xi del xj at the point C, and is defined by the limit of del f del xj at the point C1 up to Ci minus 1, Ci plus h, then Ci plus 1 up to Cn minus del f del xj at the point C divided by h as h tends to 0. For I and j equal, we use the notation diif at the point C or f xi xi at the point C or del 2f del xi 2 at the point C. In case I and j are different, we call such a partial derivative a mixed second order partial derivative of f. If we consider a scalar field f defined on a subset of Rn, then we have n many partial derivatives del f del x1, del f del x2, del f del xn. If I consider any one of them, then we can have n many second order partial derivatives and so on. So, one can easily check that a scalar field of n variables can have at most n to the power m many partial derivatives of order m. We used at most because it may so happen some of the partial derivatives does not exist. The mixed partial derivatives of a scalar valued function of several variables may not be commutative. For assurance, we cite an example. This particular example is known as the Schwarz example. We consider a function f defined over R2 as follows: f x y is x y times x square minus y square by x square plus y square if x y is different from origin and at origin its value is 0. We want to find d1 d2f at the origin. That means, we have to calculate d2f at the point h0 minus d2f at the point 0 by h and consider its limit as h tends to 0. Similarly, d2 d1f at the point 0 will be the limit of d1f at the point 0k minus d1f at the point 0 by k as k tends to 0. If we look at these two expressions, it tells us that right now we have to calculate 4 first order partial derivatives. Those are del f del y at the point h0, del f del y at the point 0, del f del x at the point 0k, del f del x at the point 0. So, we calculate them one by one. We find that del f del x at the origin equals with 0, del f del y at origin equals 0. The calculations are cited here. Similarly, del f del y at the point h0 will be h, and del f del x at the point 0k will be minus k. We have given the calculations here. So, after putting these values, we find d12f at the point 0, 0 will be 1, whereas the other partial derivative will be minus 1. This shows del 2f del x del y is distinct from del 2f del y del x. This shows that mixed partial derivatives may not be same. Now, it is time to sum up. From the above discussions, it is clear to see that partial derivatives are easy to compute. However, they fail to provide us all information about rate of change of a function in some neighborhood of that function of its domain. Truly speaking, partial derivatives give us the rate of change of the function in the directions parallel to the coordinate axis only. One can easily perceive that the rates of changes of a function f in other directions is independent of that in a particular direction. So, partial derivatives fail to be proper alternative of derivatives when number of independent variables is more than 1. We have discussed partial derivatives of a scalar field. We found that it satisfies linear property, Leibniz property like ordinary derivatives. However, if for a scalar fields all the partial derivatives exist at a point till it may so happen the function is not continuous at that point. So, if all the partial derivatives exist at a point, we are not in a position to claim that the function is differentiable at that point. In our subsequent modules, we shall try to find out alternatives such that we can say f is differentiable at a point.